My name is Joshi I'm with Los Alamos National Laboratories. I'm a high-performance computing scientist. I'll be talking about our use cases and how high-performance computing is starting to evolve to use some cloud computing technologies and how we are going to be using some of these tools to manage and maintain our systems and monitor them specifically. My name is Joshi I'm from Los Alamos National Laboratories, where I work on the high-performance computing machines. These are the supercomputers. Very close cousin to cloud computing and other infrastructure that your industries are more probably involved with. But we share a lot of same problems and trying to leverage some of the solutions that are starting to exist in the open world. And in the past, we've had to essentially write everything ourselves. But now that the rest of the world is having to deal with scale problems too, we're very happy to see that we can leverage some of these things. Before I was at Los Alamos, I was at the National Center for Supercomputing Applications. I was there for 19 years. Started in right as they were finishing up writing Mosaic, and then from there went on into supercomputing. And my area of expertise is scheduling, monitoring, data collection, and analytics. So Los Alamos, some of you may or may not know, is project or Site Y of the Manhattan Project. Right now we are stewards of the nuclear stockpile, and we do a lot of things on supercomputers that we used to do live testing, because in '92 they said, no more testing nuclear weapons live, so we had to have some other way to figure out what's safe and what's not. And we do a lot of other work for a lot of other 3-letter and 2-letter acronym groups. So what I'm going to do today is talk about, I was asked to come here and speak to you. I say, well, we're just getting started in our evaluation, but we definitely have our use cases. And a lot of things we're going to be replacing underneath and using potentially Scylla 4. So, and I must apologize, I will end up constantly saying Scylla because my Latin professor has imprinted that in my mind permanently. So, what I'm going to talk to you today about is in 2 sections. The first is how things are changing in HPC and how we're going to have to start supplying different technologies and tools to our applications scientists, such as scalable databases and things like that for the people that actually run on the machines. And then the second part, I want to jump into one of my use cases that we have to use, that we use to actually run and maintain these machines, and that's monitoring, which is a large data problem in and of itself, to where we're essentially using supercomputers to monitor supercomputers. All right, so what is HPC? We'll kind of go through this quickly. If we're looking at, a dedicated machine, we're running somewhere in the 300,000 to 1 million cores these days, 20 petaflops. So a flop is a floating point operation. And we're looking at having to deal with parallel file systems. Maybe right now one of ours is like 80 petabytes. Then we're getting, some pretty good throughput on that. These are more dedicated machines. They're not just to solve problems that are embarrassingly parallel. Most of the times our applications drive the architecture of our computers. Just to give you some idea, today's kind of speeds, if you're looking at a 20 petaflop machine, if you were to do a 14-digit calculation, 14-digit number times another one or some other operation, you do that once every single second without stopping to sleep, it would take you 634 million years to do what this machine can do in 1 second. Just to give you some scale, if that even halfway sinks in, because I've been messing with it for 20 years and it still doesn't. All right, here's 2 machines that I've worked on. The one on the left is the Trinity machine that we have at Los Alamos right now. It's about 20,000 nodes. Before at NCSA, about 27,000 nodes on the Blue Waters machine. just some pictures to see kind of what scale machines we're dealing with. The big difference between HPC and cloud computing, first and foremost, is the network. The networks are extremely low latency and very high bandwidth and very expensive. That's probably one of the biggest differences between the hardware. A parallel file system, something that we have to have and is something that's kind of more of a legacy kind of thing. And but all our codes depend on it. And right now we use Lustre, and we're getting somewhere in the order of sustaining a little bit over 3 terabytes a second writes to this file system. So cloud might not even actually need that if you have a different provisioning and distribution system. Workload, well, we deal with gigabytes in and terabytes coming out any given program, and workload, the cloud might be a little bit different. And let's see. Simulations are a big area that, of the types of applications we run on these machines. We basically create a model, give it an input deck, turn the crank, and see what comes out. Some data analytics, some of the newer type applications are a little bit different. They're more query-based. It's, hey, let's pose a question to our data set, do some statistics, and make a plausible determination. So things are changing in the world. There are different types of people coming out of college now. We're not just all computer scientists. We have data scientists, we have computational physicists, we have computational biologists, these types of things. So we're trying to make sure that we can offer a platform for them to do their science on as well. In general, a job gets scheduled on a machine, figures out which nodes the job's to run on. It says, okay, everybody, we're going to have you start at this time, and everybody tries to read from the file system all at the exact same time. And hopefully they're not too big a job, and hopefully they're not using Python that has to read thousands of little bitty tiny files from our parallel file system, because while it can handle a very high bandwidth, we can swamp it and kill it with just metadata operations. So then the job will go into its compute phase and checkpoint along the way sometimes, and then at the end it'll store its results, and then maybe it'll ship that data over to another set of machines that might do visualization or other post-processing. General workflow. One of the things that I mentioned, and one thing we're kind of looking at also, is a good solution that may be a file system that was mentioned yesterday from Scylla, could definitely help us out with. But if we were to take and say we're going to rewrite a whole new provisioning system, well, of course, we'd have to make sure all of our users rewrite their codes to be able to interface and pull from that system, and we have to budget for it and build it and maintain it. But if we put in a monitoring infrastructure, and that system can also do provisioning, which is, databases and file systems are very close cousins, maybe we can use that to distribute, this job launch data, and because it's a read-only, so we're not worried about consistency. There's some potential there, and if we had a file system-looking interface to it, boy, we could just drop that right in and run. Of course, we'd have to have some consistency sync for the times when the applications did require that. Oh, yeah, so the CWord Containers, another technology that that's migrating into our world very heavily. We're not really exactly sure how this is going to play, but it's something that's pretty much undeniable, and users right now, we create an environment, so these are the libraries, and every time we make a change to them, well, the users have to go and recompile their codes. Some of these codes take over a day to compile alone. And if we make changes weekly or whatever, it's a long waste of time because we're using this supercomputer to actually compile these codes. It's really nice for them to have their own custom environment for them because they can get everything set up the way they want. They can test it on a smaller machine, move it right up into the supercomputers, and hit the ground running. We don't have to worry about, when I launched this time, there was something odd on the machine. It was configured differently than when I was setting up or planning on. Consistent reproducible workflow. A lot of times what will happen is a scientist will run their codes, they'll go make some changes to do some improvements, come back days, weeks, months later, run it again, and they'll say, oh, I got this type of improvement or degradation, and it must be because of the things I made changes to. Well, there are a lot of other things that probably change on the machine at the same time, so being defendable in your results is also a very important thing, especially in academia. All right, obviously we have security issues, even more so at Los Alamos. We also have to overcome some of the perceived performance penalty of running a virtual machine or an extra layer. And then we also have to figure out how we're going to manage these things. So, talked about containers to talk about why, what we're doing. This is how we're going to have to do to be able to provide these new types of infrastructures and tools for our users. The legacy codes that are there, they pay the bills, they provide the dollars for making the machines, but at the same time as a site, we need to facilitate the newer generation of scientists that are going to be using and doing the computing and try to minimize what's being called time to science. Maybe we have to take one step backwards to make 4 or 5 steps forward. All right, virtual cluster architecture here. This is kind of how industry roughly does things. You might have a bunch of virtual machines and you'll, on Amazon, go grab a bunch. Not exactly how things kind of work in our environment, or probably will. And what happens is when you request an allocation on the machine, you'll get so many nodes, and then we'll probably do more of a one-to-one type of build for these things, for your machines, and distribute them up however you need for your application. And while that's going on, there's obviously other jobs out there doing other things. And I did note this morning, subliminally, I must have thought about the sea monster because the scalable database looks, the geometries look a little bit like they're the guy. So another thing that we have to do, we have to go to, just show you the links that we have to go to get performance. We put burst buffers, which is nodes full of SSDs that stage application data close to the actual compute nodes. So that's a whole job in and of itself to do staging. Another thing we're looking at doing is rolling containers underneath the machines and prepping them so that when it does go to load its libraries, Python or whatever, I mentioned that because it's a big culprit. We're prepping that all ahead of time, so it's all local reads and writes. A lot of work just to solve some of these small problems that we're hoping some of the newer tools can help us avoid. So that was the first quick part. Now we're going to step into the second one, shift gears a little bit. So if you're sitting next to a millennial, explain to them what this is. Section 2. We have to manage and maintain and run these machines. So my father-in-law, who was in banking for many, many decades, would always say, if you don't monitor it, you can't manage it. And that is so very, very true, especially with this class of machine. And everything along the lines has to scale, from the collection to the aggregation to the storage, how you query it, and even how you look at the data. We're primarily concerned with a number of classes of data, events, syslog, something happened at a certain time, and I'm going to talk briefly about some of the things we've done and tools we've written for processing those metrics. We're talking time series data here. What was the load on a certain machine at a certain time? What was the bandwidth in this direction or this segment of the network? Memory usage, on and on and on. And then context as well. Context is what job was running on this machine at that time, and why are these metrics relevant? All right, we also have to provide this data to a number of different user types. The admins, they're always looking to say, what's going on the machine? We need to know if something is going well or going bad. You know, the users always want to know how did I utilize the resources on which my job was running on. Code developers are always looking to improve their code, identify bottlenecks. System designers are looking to build the next machine. And researchers, who knows what they really want? Maybe to find the Holy Grail, I don't know. What's the saying is like, if I knew what I was looking for, I would have already found it. So there's some interesting research in this area that I've been a part of. What we have to deal with, our use case, logs, we're looking at somewhere in the order of tens of gigabytes a day, which is not overly huge. Most of our compute environments or OSs are stripped down, so they don't have a whole lot of software extra on them, and so they're not very chatty. But sometimes it can burst up to hundreds of gigs a day. And on the other side of the fence, we have metrics. Say on the Trinity class machine, we're looking at 20,000 nodes, maybe 200 metrics per snapshot. So that's about 4 million metrics a second if we're collecting every second, and that ends up be about 4 terabyte a day. And we can easily step that up to like 10 hertz, so make that 40 terabytes a day. We also have not just one system, we have 12 to 15 systems. Granted, not all of them as big as Trinity. So these are the types of data that we need to take in and do something with. So what we do, excuse me, is first thing is visualize. Visualize what's there. Don't make canned assumptions. Visualization leads to understanding. That leads to automation. We've spent so much time looking at and thinking that, hey, there's some machine learning thing that we can just throw data at and it will just tell us what all our problems are. Seems still a bit pie in the sky. For example, this is the cabinets, bird's eye view, and showing the temperatures, the cabinet temperatures on the Blue Waters machine. If you'll see down here, we have one standout. An outlier analysis or a simple threshold would show you this. And you would get an alert saying, hey, this cabinet is too hot. We better do something about it. But unless you visualize it, there's a lot of other things happening here that you might not pick up on. For example, on the far left row, there's an area that's relatively warm. Why is that? Why is that particular area higher temperature than everywhere else? So, well, there's actually door, and we had to do with the data center cooling systems there, and airflow, and a number of other things. But the other thing, if we take a look closer down at the standout that we obviously hit earlier, if you look around it, everything else around it is much cooler than the norm. So what was happening there is a filter had plugged, the cabinet got hot, but with that plug, it caused higher pressure and a higher flow rate in the neighboring cabinets. So just seeing things helps you understand what's happening. Workload throughput, this is something we take and look at our jobs flowing through the system over time. We call this a ribbon view. The ribbons, the color bands, are sized based upon the number of nodes in a job and flows over time. We look at just some of the largest ones and then aggregate all the super small jobs into the white icing on top of the cake. The right side is how they're laid out on the like a 3D torus, the Gemini network. So we can see our geometries of the jobs because that makes a difference based upon the speed and the network itself. So just being able to see what's going on. For example, if this was actually the case and this was some point in time and all of a sudden all the jobs stopped at one time, well, something happened and it would be of serious note. All right, another thing we do is a machine learning analysis where our logs flow in. There were 2 projects, one NSF, one DOE, called Hilo, the other Baylor. And what they did was would build their own template library from the system logs that come in and create a pattern, a library of patterns that we could use to analyze the flow and do matching as they came in, and we would tag it with an integer ID. Well, doing that made a lot of things, reasonable to do. Before, if you just have lots and lots of logs, you have to go through and do string processing on them every time you want to touch them. Now you've boiled it down to this particular thing happened at this location at this time. So now we can do macro events. We can look at fingerprints, things that happen together, how events correlate, how they cascade, how they move through different parts of the system. And we start doing event prediction. One of the things we look at with the logs, this is a clip from a white paper of mine. We notice in that little area 2 over there, there's 2 zones where these are run times of an application, and they vary. Consistency wasn't so great, so we were trying to figure out why. And so we looked at, there was a marked cliff right there with the slow and the fast. Well, what changed? Obviously something changed. What happened? So we go to the logs, and since we have them tagged, we can just do database mining to say what happened in the slow period that did not happen in the fast period. That's quick and easy. But also not just what happened and what didn't happen. Maybe things happened in different counts or at different rates. So when you sort these, you get a list of culprits to help aid you in your investigation of what happened. If you want to see what a big flow of logs look like, you can also take and plot them over time. Every vertical column is a second, and every row is a different log message type. So when we start looking at that and we put a gradient on there, a color gradient, tell you how many of that particular log message happened at that particular time. And you can see here we have some red and yellow bands saying like these log messages were happening at a much higher rate at this time. Or maybe we'll see over here a vertical stripe of lots of different messages happening at the same time. So these are types of things that you can just start looking at and understanding what's happening. And of course this leads to automating and looking at fingerprints and prediction, because we see some things happen, we can calculate the probability of another thing happening. Of course, this is all data mining. This is one of our use cases where we want to put this data into an engine that we can really look back over years and years and across different machines. So one of the things that we were able to do is take these events, see how they correlated in probability, time, that type of thing, and we can find these event maps, patterns, how things work. And uniquely, we built the system. We really didn't find anything that was like, butterfly wings to say, uh-oh, we saw this little thing happen here, and weeks later, something was going to crash. The machine just didn't happen to work that way. But we were able to validate the engine because we found that log messages that were emitted from cron jobs do predict themselves very, very well. So to bring it kind of all together, we've written tools, machines are getting bigger, and we need something underneath to provide data to the tools that we've created. We're also looking at creating more and more tools to do different types of analyses on the fly for these machines, because as they get big, we need to understand them even better. And that comes down to monitoring. It also comes to helping us provide services to our users, the people that run on the machines. So we have to look at provisioning and job launch. That's a big scalability bottleneck. Monitoring. We have to put we have a lot of data. We have to put it somewhere, and then we have to be able to access it. So that and our visualizations themselves have to scale. So one of the things that HPC and the cloud computing world, we definitely need to continue to leverage each other's successes. And kind of an analogy I use to explain it is like HPC and cloud computing are kind of like teen siblings, maybe not always get along. They share a lot of clothes, but they play different sports at the end of the day. And at the end of that day, it is very good to come home and have dinner together and figure things out and do some sharing. So with that, I'll happy to take questions.